Okay, and welcome to the second half of Chapter 11. We're going to encounter some math here, which, and some of you might hate it, but it's one of those things you got to do. Okay, so mole fraction and molality. These are different ways of talking about concentration. Now, you should have already seen molarity before, where molarity is the number of moles of solute per liters of solution. Mole fraction and molality are two different ways of measuring concentration. Mole fraction is the number of moles of one of the components of a mixture divided by the total number of moles of stuff, of all the things in the mixture. Okay. So, for example, say you have the worst cocktail ever. It's a mixture of water and ethanol and sodium chloride. Okay, that's just water, alcohol, and table salt. If you had, 3 moles of water and 2 moles of ethanol and 1 mole of sodium chloride, okay, what are the mole fractions of each of those? Well, you need the total number of moles. That's 3 plus 2 plus 1 for a total of 6. That's the easy part. Then you have the mole fraction. And so the mole fraction of water is the number of moles of water divided by the total number of moles. So 3 divided by 6 is 0.5. Mole fraction, even though it's calculated in the same way as a percentage, it's not reported as a percentage. It's always just reported as a fraction from 0 to 1. Because unlike a lot of other things, mole fraction was developed after people got sensible about percentages and started to think of them and report them just as numbers between 0 and 1. That swoopy-looking X, that's not actually the letter X. That's actually the Greek letter chi, spelled C-H-I. There's almost certainly a reason for why they use the Greek letter chi to talk about mole fractions, but I don't know what it is. But just remember, it's chi. Swoopy-looking X. Okay, so mole fraction of ethanol, ETOH, is going to be just 2 moles of ethanol divided by 6 total moles, or 0.33. And the mole fraction of sodium chloride is just 1 mole of table salt divided by 6 total moles, or 0.17. And there are various reasons to do this. It's a handy way of talking about mixtures. So, for example, you can chart it very straightforwardly. So here we have just a simple chart showing the mole fraction of ethanol along the bottom, going from 0 to 1. And how much fun is it to drink this ethanol drink as you go from 0 to 1? 0 is just pure water, so that's no fun. And as you go along, the amount of fun you get to have by drinking this ethanol increases until you get to a mole fraction of about 0.4. 0.4 is 40%, or 80 proof ethanol. That is, the strength of your standard shot of vodka. After that, though, as the drink gets stronger, it gets less fun to drink until you get to a minimum, not 0, a minimum near around 100%, or pure alcohol, grain alcohol, as it's known. That's when you get to have fun because you get to prove how badass and tough you are being the dumbass at the party. But it burns. It tastes like burning because you're drinking pure poison. And like I said, this is a measure of fun. And not coincidentally, it's also a measure of how bad the hangover is going to be the next morning. Because it turns out that part of the reason for your hangover is because you're dehydrated, because you've been drinking poison all night. The other part of the hangover is because of other stuff mixed in with your drink. So the less your drink tastes like evil, the worse it's going to hurt in the morning. It's just one of those weird things. All right, now let's move on and talk about molality. Okay, molality. Okay, molality is it's another measure of concentration. It is the moles of solute per kilogram of solvent. So moles of A per kilogram of B. Okay, so say you have 0.825 moles of sodium chloride dissolved in 750 grams of water. Well, 750 grams, that's 0.75 kilograms. You dissolve that, it's 1.10 molal. Yes, molality is very similar to molarity. The units are molals versus molars. It was invented to be very similar to molarity, which is, kudos for effort, but it makes it hard to talk about these things unless you over-enunciate things and say things like molal and so on. But, that's just one of the things you do. Now, molarity is always going to be very, very close to molality, because molarity is moles of solute divided by liters of solution. And so for that same solution, you'll have 0.825 moles of sodium chloride divided by almost 750 mils. It's not going to be exactly 750 mils. It's going to be very close. And so you're going to have a molarity of about 1.10 molar. Not quite, almost, a little bit less. And so they're always going to be very, very close. And you might be wondering why the hell we need these multiple measures. Why do we need mole fraction and molality and molarity? Well, the advantage, molarity is very easy to measure in the lab. You need volumetric glassware, you measure the one substance, the solute, and then you can just put it into, very good glassware, and boom, you're done. Just 2 steps. But molarity is inconvenient for measuring things that change across temperature, because volume changes with temperature. Okay, so here's your graph. As you increase volume, you increase temperature. For any substance, you increase temperature, the particles move faster, they bounce off each other, they take up more space, the substance gets bigger. Not necessarily a heck of a lot bigger, but it's there. And so molarity is going to decrease with temperature as the volume of the solution gets bigger. So you'll have more moles across a larger volume. So a solution will go down. That's just the way it is. And for a lot of things, we want something that is temperature independent. Something that, it doesn't matter what temperature it is. And mole fraction and molality work for that. You have a mole fraction, it's going to be the same at 4 degrees as it is at 96 degrees. Same for molality. And that's just not true for molarity. It's not a huge difference for molarity, but it's there. And if you plot something as a function of molarity, you will see the swooping changes from those changes in volume. That you wouldn't see those weird changes if you were plotting it against molality and mole fraction. And for the things we're talking about next, the colligative properties, we're talking about things that take place at different temperatures. So it's important to have something that is temperature independent. So you're going to need to recognize those for that reason. And the other is that people do use these. That chart I showed you for alcohol versus fun, okay, that was kind of a silly little chart, but we very often do plot things as a function of mole fraction. It is a very handy way to plot it. And it works for solid solutions, liquid solutions, mixtures. It works all over the place in very handy ways. So it's definitely, mole fraction is very widely used. Molality, not as much, but it still does show up, and it is helpful to have that on tap as well. Okay. So let's move on from these. The math is fairly straightforward. Do practice, 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 practice. Get good at working with mole fractions and molalities. But let's move on. Okay, so our colligative properties are the properties of a system that change based upon whether things are dissolved in the system. So that would be things like the vapor pressure of a liquid, its boiling point or its freezing point, or what's called the osmotic pressure. And if you have things dissolved in the liquid, all of these properties are going to change. Now, vapor pressure is the pressure exerted by the vapor coming off of the liquid. Okay. So let's go ahead and imagine, okay, here's another one of those chi-charts, mole fraction charts. Okay, here's water going from 0% water to 100% water, assuming it is, got like something like table salt dissolved in it, right? So as you go down to 0% water, the vapor pressure of the water is going to decrease just because there's less water present. Okay, more water present, just more pressure exerted by the water until you get up to 100%. And that is going to be perfectly reasonably true. I mean, table salt, NaCl, does not have a vapor pressure. Okay, it melts at hundreds of degrees Celsius. It's just not going to exert any sort of vapor pressure. Okay, all the pressure coming off of a sodium chloride solution is going to be from the water, and as you get down to pure salt, it's going to go down to zero pressure. Okay? And it really is a straight line like that. That is what is known as Raoult's law. Okay. It's just that the pressure exerted by a fluid or a liquid is equal to the mole fraction times the pressure exerted by the pure fluid. And, that's just a nice linear relationship. If you think back to your gas laws, that will probably look an awful lot like Dalton's law. In fact, it is exactly like Dalton's law. Dalton's law of partial pressure says that the pressure exerted by a gas is independent of, the other gases present. This is more or less the same thing. This is just saying how many moles of the liquid are present. Okay, the fraction of the pressure exerted is equal to the fraction of the gas that's present. It's very similar. And so you can use Raoult's law to predict the pressure exerted by a mixture of liquids. Here we have our old standby, water and ethanol. You'll see, they look sort of exactly opposite one another, just because if you have 0% water, you have 100% ethanol, and vice versa. I've tried to draw the pressure exerted by the ethanol as being slightly different from that of water. Ethanol is a little bit more volatile, so it's going to have a higher vapor pressure. And so, as you go from pure ethanol to pure water, the pressure exerted by the ethanol is going to come down to zero. And the pressure exerted by water is going to come up. And each one has the same sort of Raoult's law line. The pressure exerted by that fraction of the liquid is equal to the pure vapor pressure multiplied by its mole fraction. And so the total vapor pressure exerted by the mixture of the liquids is just the sum of the two pressures exerted by each liquid independently. And it gives you a line that looks like this. It's just a straight line going across from one pure vapor pressure to the other. It works out very nicely that way. And that line is just the sum of those two Raoult lines independently. Now, does the actual pressure look like that? Hell no. There's always going to be some sort of deviation from Raoult's law. For a mixture of ethanol and water, it's going to be a line like this. It swoops down beneath the ideal line. And that's just because water and ethanol are very similar to one another, and they're attracted to one another, so they stick around in solution rather than going up into the gas phase. You see deviations like that for every mixture, but some of them are going to be a positive deviation, some of them are going to be a negative deviation. That is to say, some mixtures will exert less pressure than Raoult's law would predict. Some mixtures will exert more pressure than Raoult's law will predict. And you can guess which way they're going to go based on what sort of liquids you're looking at. If you have a happy mixture of liquids, then they're going to exert less pressure. That is to say, sort of like how like dissolves like. If you have two liquids that are very similar to one another, then they are going to want to remain as a liquid mixture together. So, for example, water and ethanol are both polar compounds, so they are going to remain as a liquid. They're going to have a negative deviation. They're going to exert less pressure than you would expect. Whereas if you have an unhappy mixture, like oil and water, things that don't want to mix, then you're going to get a higher pressure, a positive deviation from Raoult's law. And that's really all we're going to do there. I'm not thinking we're going to do too much math with mixtures of liquids, but some conceptual sorts of stuff. You can expect that. Like what sort of deviations would you expect? Would you expect a positive or a negative deviation? Things like that. And I have gone over 15 minutes, so I'm going to go ahead and call it, and we will finish up colligative properties and so on in the next lecture.